Sure. All right, everybody. Class recording has started, so yeah. To answer your question, yes, I can give you a practice one. Yeah, I have access to a lot of them. Let's go make sure we go through all these things and then we can start. All right, so Unit 6, like I said, talks about circular motion and universal gravitation. We usually put those two things together in the context of like planetary motion and that gravity makes things go in a circle and stuff like that. But the beginning part of this unit deals with things moving in a circle. So in order for something to move in a circle, it requires a force because it is accelerating. Why is something moving in a circle accelerating?
Because it's
changing direction, right?
And when it's changing direction, it's accelerating.
And so in order to get something to change direction, right, the force has to act on it in a very specific way. If the force is acting on it in the same direction that it's moving, it will speed up. If the force acts on it on the opposite direction from the way that it's moving, it will slow down. But if the force acts perpendicular to the motion, it will not speed up or slow down, but it will change directions. Okay? So always important that that force acts perpendicular to the current velocity. All right? But in terms of a circle, right, that means that a force always has to point towards the center of that circle. Okay? So for question number 1, a ball is tied to a string and rotated in at a uniform speed in a vertical plane. So it's going up and down, right? Just swinging it like this. The diagram shows the ball at its lowest position. Which arrow shows the direction of the net force acting on the ball? All right?
Good answer.
Why does it have to be A? Centripetal force points towards the middle, right? Okay. So there has to be a net force acting in that direction. There may be other forces acting on the ball as it's swinging up and down. And in that case there's gravity. But the net force has to be towards the middle because it is accelerating. No, it has, so in this case, right, these are representing net forces, right? But you said if we draw this, okay, so there's the ball at the bottom of the circle, okay? This picture is this demonstration, right? Ball tied to a string in a vertical circle, okay? So there are two forces acting on the ball, right? You have gravity, right? Remember that net force is a combined effect, right? If we're drawing just forces, no. Well, let's draw forces first. What's the other thing that is affecting the ball?
Gravity.
What's the
net
other
force?
thing? Tension, right? There is no normal force because there's nothing underneath it, right? Okay? But there is a string that's going this way, okay? The combination of those two, the net force, has to point towards the middle. So which one has to be bigger? T has to be bigger than W in this case. Okay? Does that make sense? Now, if we flip it over, right, and go to the top, right, there's still a weight force acting on it. And it's exactly the same as this weight force. Right. In this case here, the total has to be the same here. So in this case, T is smaller because the weight force is adding to the total, whereas at the bottom, the weight force is subtracting from the total.
And that's where they say pick which one. Like they say, which of these positions of the circle has the greatest potential energy? If you have a vertical, swinging vertically, like on a Ferris wheel, right?
No, not, this,
Like which one?
this unit wouldn't ask you about potential energy.
Oh,
It would ask,
yeah. but
yeah,
that's what I'm
because of
saying.
height though, that doesn't have nothing to do with the tension though.
Yeah.
So if they ask like which part is greater,
The greatest net force would be neither, because the net force always has to be the same. If it said which one has the greatest tension force, I would say the bottom, because the rate has to make up the difference. Yeah.
I'm sorry.
It's okay, I thought something was crumbling or blowing over there or something like that. Does that make sense? We good? But the net force always has to be towards the middle. All right, particle with mass is moving with a constant speed in a uniform circular motion. What is the total work done by the centripetal force during one revolution?
What?
aced it. I'm gonna do so well on this test.
So, centripetal force. We said, how does centripetal force act in relation to the motion? Perpendicular, right? But when we talked about work, which we did a couple days ago, right? What component of the force does work? The parallel component is the only one that does work. So in this case, because the centripetal force is perpendicular to the motion, it does no work, right? Also, right? What is that telling you about the energy?
It is constant.
It is not what?
Different.
If there is no change in the energy, there's no work.
Huh?
Because not true over.
Oh, yeah, because work is energy done in a certain amount of
But
time.
if it did
That's
still,
power.
but if it
I hate
would
it.
still have, if it had like, if it was accelerating with it.
Now, it's accelerating, but
But it's
Ki-
still perpendicular.
but kinetic energy is not changing because the speed isn't changing. Okay? Now, do we want to get complicated or do we not want to get
Please do,
complicated?
because I don't understand
Okay,
work.
so, in this case, all right, there is a change in energy. What kind of energy is changing? As I
Potential.
swing it this way,
Potential.
the potential energy is changing. Okay, but the potential energy is changing not because of what the string is doing to it,
No, it's the surroundings.
because of what gravity is doing
Like the
to
surrounding
it.
energy.
Okay, the string is still acting perpendicular to the motion, so the string does no work on this ball. Okay,
It's
Does
just,
that-
it's
does
just
that
kind of
make
doing its own thing, like,
well, the gravity is making it go up and down.
the gravity
It's just like,
affects,
it's kind of like canceling out. Like the string's making it go in a circle.
but the only energy
Yes.
acting on it is on a vertical axis.
But in this case,
So,
is it, so, the only type of energy that's changing in this case is what? If I spin it at a constant velocity, is the kinetic energy changing?
no,
No. It's going up and down, but its kinetic energy isn't changing, right? So therefore, the force that is changing the velocity, no. What force changes the velocity in this case?
wait,
Nope. My hand isn't touching the ball. The tension force changes the velocity. But how does, no, because how is the velocity changing?
it's changing in a circle.
It's only changing direction. It's not speeding up or slowing down.
It's
Does that make
directionally
sense?
accelerated.
So it is a little confusing.
But what, can you define work, like, because I said work is a amount of energy put into a certain amount of time.
That's power.
What is work?
Work is the amount of energy put into something. That's two different things. Work is a total amount of energy that changes. Power is
Oh.
energy over time.
So then if it's a constant speed, the string has nothing to do, so it's never gonna have any work.
Right. The string isn't changing the energy of this ball. because the string isn't making it go faster or slower, and the string isn't making it go up or down. Okay?
The only thing making it go up and down is gravity and your hand.
Yep. Well, no, not my hand.
Oh.
So,
But gravity.
so
then.
technically, gravity is the only, on the way up, getting back to some basic concepts, right? When it goes to the bottom, which way does it want to go?
Down.
No. That way.
Oh, straight. I'm such an idiot.
So it wants to go in a straight line, right? Inertia says straight line. So it goes in a straight line, or it tries to go in a straight line, but what keeps it from going
The
in a
tension
straight line?
of the string.
This keeps it from going in a
Or
straight
the
line.
string's length.
Centripetal force, right?
Yes.
So now it just changes its direction. Now the ball wants to go this way, right? Does it again. What's actually making the ball go upward? Inertia is making it go upward.
Oh.
Does that make sense?
So it's not your hand.
No.
But why is your hand moving a little bit when it's going around?
That's just because it's not a perfect system. Right?
Okay. We're just talking like in a vacuum.
Right. Yeah. So actually, inertia is responsible for taking it up, and then gravity brings it back down. Okay. Gravity plus inertia is responsible for going that way.
That's really cool.
But gravity, like we talked about, gravity doesn't change the energy of something, it just changes its form. Potential up, potential down, potential up, potential down, right? The string, because of the whole perpendicular thing, does no work on the ball. Because the string doesn't change its energy. The string doesn't make it go higher. The string doesn't make it go lower. The string doesn't make it speed up. The string doesn't make it slow down. The only thing the string does is change its direction.
Inertia string work.
Inertia doesn't do work. Inertia just is. Yeah, right? Yeah.
It's just a property of life.
So
And-
it's just like maintaining it, right?
Wait, what did you say?
Yeah. It's, what do we call the fancy word for maintaining something in physics?
Oh.
It's conserving it, right? Gravity conserves the energy. It turns it into something else, like it turns it in from potential into kinetic, blah, 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 but it doesn't actually change the amount.
There's so many words like this in the back because like
Air resistance, yeah, throws this whole question off, but that's not where they want you to go with this. Yeah, friction, air resistance, they don't want you to go there. Okay. But does it make sense why the string doesn't do any work, right? Because of the whole perpendicular to the motion thing, okay? It'll change its direction, but it won't cause it to speed up or slow down. All right, ready?
Yeah, I'm always ready.
Hopefully this question is easier because of what we've talked about before. Right?
Particle P is moving anti-clockwise. Oh, wait, wait.
Force is that way.
Yep. And the force has to be in the same
Is that
direction.
co-tangential?
This V is the tangential velocity. If we got rid of the acceleration, what would the ball do? Just go that way, because that's what velocity is. Velocity, inertia sort of represents its velocity, right? You know, going in the same direction, doing what you want it to do, doing what it was doing before, okay? But velocity and acceleration always have to be perpendicular, just like velocity and force have to be perpendicular, because acceleration is caused by force. Okay? Good there? All right, so let's go here. This question is about circular motion. Thanks for telling us. A ball of mass 0.25 kilograms is attached to a string and is made to rotate with a constant speed v along a horizontal circle of radius 0.33. The string is attached to the ceiling and makes an angle of 30 degrees with the vertical. So, something like this. Right?
It's not only live here, just a little bit.
Okay. All right. A1. In the diagram above, it's not above because I needed to move it over so we had some more space, right? Draw and label arrows to represent the forces on the ball in the position shown. This is actually a little different, all right? So, what's one force that we can put on this drawing right away?
Acceleration.
Acceleration is not a force.
Velocity.
Velocity is not a force
Oh
either.
my god, what am I thinking right now? I'm thinking units. I hate myself. Alright.
Okay.
Net force.
Got that.
Tension.
All right?
Tension.
And then tension. Tension comes from what?
String.
The string.
Which is the
So,
hypotenuse in this case.
this is going to be the tension. Wow.
New theory.
All right. So, that's that. That's A1. That's 2
Net
points
force.
right there. Net force is a combination of forces, right?
Yeah.
So, state and explain, for part 2, state and explain whether the ball is in equilibrium. No, that's 1 point.
Nice.
Okay? But it's a 2-point question though. Right? Okay? The ball is not in equilibrium. Why is it not in equilibrium?
Isn't it because it's in constant motion?
What is our definition of equilibrium?
Isn't it when every...
Net force is 0, so if net force is 0, what else has to be 0? Acceleration needs to be 0. Is acceleration 0 in this picture?
Oh, no.
It is not. It keeps doing what?
Changing direction.
Changing directions.
So,
okay?
no,
This
because-
object is not in equilibrium because it is accelerating. It keeps changing directions.
That's 2 puntos, or 2 marks.
That's
as
your
they like
two.
to call it.
That's your 2 points.
Marks.
Okay? Or your 2 marks.
Sorry. We gotta go with the scheme.
All right. Good with those?
Are we doing B?
We are doing B, yes. All right. So determine the speed of the rotation of the ball. We said that the force that points towards the middle, the force that causes the change in direction, is called the what? The centripetal force, right? And the centripetal force the amount of centripetal force is determined by the mass, the tangential speed, and the radius of rotation. Okay?
So we have to calculate speed
We have to calculate speed.
to
So,
get FC.
in this case, no. This one says determine the speed. So
And
you're,
rotation. Okay, never mind. I'm an idiot. Alright.
okay. So I just rearranged that equation, right, to get V by itself.
We can find centripetal force with formula, right? We have enough stuff.
Do you? Okay, we have an R and we have an M, right? But we don't have a centripetal force here.
So we can calculate.
Yes, we can calculate it. Okay. First, is W equal to T in this case? No, it's not. All right. 2 reasons. 1, they're not right up and down from each other, right? And 2, they couldn't be because what was the answer to A2? No, right? When we have forces at an angle, what do we do? What do we have?
We have a
Break them.
trigonometry
We
formula.
have components, right? We have this component
Calculus.
and we have this component. I'm gonna get rid of T here and move it over here. Okay? All right. So the acceleration is occurring horizontally as it changes directions. Is the ball moving up or down? It's not. Does that make sense? Right? Ball's not moving up or down. So what's true about those up and down forces? They have to balance. Okay? Does that make sense? That this and this have to be the same. Because it tells you that this is a horizontal circle. Right? Yeah, so we can figure out what this weight force is, right? Okay. And anybody have the calculator out? No. All right. It will help us to calculate this if we have our calculators out. So, phone calculator is perfectly fine. because I had my calculator out earlier today, Fuad.
Jeez,
So-
call it loud. Come on, Fuad.
All right, so we know this, and that means that this has to be 2.45, okay? But that's not what force we want. Is 2.45 the centripetal force?
No.
This one is the centripetal force.
Okay.
Okay? We know that this is 30, and that means that this is 30 as well. Okay? So now we're going to do some trig, right?
The trig. Trigonometry.
Because even though it's up here, we just moved it, because this one points inward, that component is what?
Centripetal.
That's the centripetal force, because it points towards the middle, right? So we can call this f of c if we want to. I rounded to 1.42, but yeah, same thing. So. And then, that goes there, right?
IBPHYS2.
That was extremely full.
Wait, is today Wednesday?
What?
Today's Wednesday?
Today's Thursday,
Oh.
so.
I think tomorrow's Friday.
All right, we'll finish this up and start chapter 5 tomorrow. Woo!